Sick. Give you A in return. Okay. Your effort evaluation, thank you. So, yeah, right now, I think the fill out rate is less than 10%. So let's try to target making it higher, yeah? So making it at least 80% on fill out rate only. How many models are recommended for us to create in assignment 2? How many models? 2 to 3 models, and each of the models you will have multiple experiments. Do we need to include acknowledgement in assignment 1? Yes, you need acknowledgement in assignment 1 and 2. Hello. Okay, sorry for the delay earlier. So yeah, let's get started with what we need to do today. Can we modify assignment 1 when doing assignment 2? Yes, you can modify assignment 1 before the due date. Are you well? I am okay. I'm okay. Right. So yeah, let's get started with what we need to do today. So in the past 3 weeks, we have covered 3 classification models, namely decision tree, logistic regression, and support vector machines. So today we are going to talk about a concept called ensemble models. So these ensemble models, it's a mechanism on how can we bring all of those models that we have learned together so that they will perform better. They would outperform one another and cancel out the error between each other. So for today's lecture, what we are going to do is ensemble methods. We are going to go over some general concepts of ensemble models, ensemble techniques, especially on bagging, boosting, and stacking. So bagging, boosting, and stacking are 3 of the common ensemble techniques that is still useful in today's world. So this ensemble model has become very popular since in the past 2 decades, and now they are still very relevant even though neural networks have become more and more popular. Yeah. So if you are familiar with Kaggle and the competition in Kaggle, you can come to realize that most of the models or most of the people who win the challenges in Kaggle, they are usually utilizing the technique called ensemble methods. So this ensemble method is practically a general concept of how can we use a group of weak learners that come together to form a stronger learner. That means making our machine learning algorithm slightly better compared to when they are being used separately. So this is the general concept of what ensemble model is about. So this is just a formal way of putting things into words. So ensemble learning is a machine learning method in which different learning algorithms, they are trained and combined to make the final prediction. So now how these different algorithms are being put together and how do we make use of all the prediction to reach to a final decision point is ultimately what we are going to discuss in today's lecture. So this ensemble method, they do not rely on any single model. So that they do not rely on any single model. That means what we are trying to do here is to train multiple learning models to compensate each and other's weaknesses and bias. So here, our aim is focusing on creating more precise prediction to to improve the overall accuracy and also the robustness of the entire predictive system itself. So the hypothesis that we are trying to make here is really that different models will make uncorrelated errors. That means every single model that we put in to this ensemble model, we are assuming that they will make very independent errors. So the error that they make should not repeat from one another. Therefore, this ensemble is expected to cancel out the error that each model has made. So this is the general idea of of ensemble model. So now what it means here is that just imagine when we have a MRI scan image. So now what happens in real life is that we will take this MRI scan to be interpreted by 3 different medical doctors. So now 3 of these medical doctors is going to read this MRI scan to decide whether this patient has tumor or does not have tumor. So then, at the end of the day, we will arrive at a unified decision on whether this patient have tumor or do not have tumor. So now what we are trying to do here is to borrow the same idea to put into machine learning. So how can we package this different machine learning algorithm together so that every single model here will make its own prediction? And at the end of the day, how can we figure out an algorithm to provide one final output? So this is what we are going to discuss in ensemble model. So when our predictions from multiple models are aggregated intelligently by using some smarter means, the error can get to cancel out while correct prediction can get to be reinforced. Okay? So today we will be discussing some of the idea of how can we make use of bagging, boosting, and also stacking to cancel out the error from one model to another. So as a result of this ensemble model, what happens here is we are trying to overcome some common issues like, for example, overfitting, underfitting, excessive variance, as well as susceptibility to noise, as well as anomalies. So what we are trying to do is to reduce the impact of every single algorithm on these aspects. So this ensemble learning, it makes prediction based on a number of different models. So we are finding some ways to combine different algorithms in making one huge machine learning model. So what we are trying to do is trying to make this algorithm to become less data sensitive in order to decrease variance. I hope you still remember your bias and variance curve. So how can we collect all of the decisions made by different algorithms, which then helps to prevent the bias of any single model? Okay? And finally, this will help to improve our prediction. And this idea that we are discussing today on ensemble models is applicable to both classification and also regression methods. So you may be thinking, how can we combine the prediction for any machine learning algorithm? So in 2 cases, if we are doing classification, we will then undergo a process called voting. So all of this model is going to produce one predicted output, a class. And what happens at the back end is we will have some voting mechanism to select the best predictive outcome and produce that outcome as a result of ensembling. As for regression, this aggregated prediction will then be represented using average methods. Okay? So say, for example, these multiple models will give us different values. And right now, in ensemble, what we are trying to do is to take the average output of every single model produced. So these are some of the ensemble methods techniques. The three most common ones are bagging, boosting, and also stacking. So now, what to take note on in this slide is that you want to take note on the data set that is fed into this model, and also how this, which represent how these individual learners are being trained, and how their predictions is being combined. So now in bagging itself, what we are leveraging on is one type of base model. So one type of machine learning model being trained on multiple sets of training data. So at the end of the day, the output that it predicts is a voted prediction. So as for boosting, we are also looking at one type of base model that channels from one to another. So now the training data of each of this model are channeled from one to another. So the output of the first base model will be channeled into the second base model, which then the output of second model will be channeled into the input of the next model to reduce the error which is made by the previous model. This is boosting. So every single training data for the subsequent base model here is called the weighted training data. Okay, so say for example, the first model can make some error regarding its prediction. So now this error is going to be weighted more heavily for the next base model. So this next base model will then focus on the wrong prediction that the previous model has made to make it right. And therefore, with this boosting process, it is making the prediction a little bit better as in it cancels out the error which is made by the previous model. Okay, so at the end of the day, we are getting one predicted output. So in terms of stacking, this is the most advanced one. So what it does here is we are combining multiple types of base model. So now we will say, for example, it is we can use SVM, decision tree, as well as logistic regression as our base model to train on the same data set. So at the end of the day, the output, the predicted output of all of this model is going to be the input of the following meta learner, which will then make the final prediction from the output of the base model. So now this is how stacking will work. At the end of the day, we are producing one predicted output. So we'll go over some of the working principles in the following slides. But this is the general idea. So as we cover three of these ensemble models technique, you will come to realize that there are two major types of ensemble methods. So one type is called the homogeneous method, and then another type is the heterogeneous method. So both of these differ by a mixture of models that it is taking into its package itself. So the first two types, bagging and boosting, they are homogeneous because they make use of one single model that is repeatedly being utilized. So what this every single model receives are different sets of training sample. And we'll go over what are the differences between the different training sets that each of this model will receive in a bit. So as for stacking method, it is a type of heterogeneous ensemble method. So heterogeneous here refers to a mixture of different models that we put together in this ensembling process. Each of these models will receive the same set of training sample. They are just being trained on different algorithms to produce different output, which then this output will then be used to create the final predicted output. Okay, so the homogeneous and heterogeneous here in the ensemble method refers to the mixture of models that it contains in one ensemble. So now, as a summary, ensemble models, is the ability to combine multiple base models to produce a more accurate and robust prediction. So how they work is by reducing the variance and bias of the overall prediction, and they can be homogeneous or heterogeneous based on the mixture of model which we are putting together. Any question? Is that clear? Okay. It can sound very difficult, but it is actually not so hard to understand when we come to discuss the detail. Is RF a type of ensemble model? Yes, RF is a type of ensemble model that falls into bagging, bootstrap aggregation. Okay, so before we moved on, ensemble methods are generally used to improve the performance, accuracy, generalization of a model. So now first we want to talk about the first type of ensemble model, which is bagging. So bagging is a short form for bootstrap aggregating or bootstrap aggregation. So in the following section, what we want to go over are some of the working methodologies, benefits, and also some limitation of bagging. So this is the general idea of bagging. Bagging is also known as bootstrap aggregating. It helps in reducing the variance and improve the prediction stability. So now what does this bootstrap aggregating refers to? So bootstrap aggregation refers to how do we select subsets of sample as the input of our training data for our base model. So now, say for example, we have one set of data. We are going to have multiple bootstrap samples that is being channeled to every single model. So now say for example, in this illustration here, our base model is decision tree. So we have multiple decision tree, whereby each decision tree is going to receive one set of training sample to train and to produce a predicted output. So at the end of the day, we are having multiple predictive output depending on how many decision tree or base model do we include in this assembling process. So at the end of the day, if let's say this is a classification task, what we are going to use to produce the final prediction will be through a voting mechanism. So we will figure out how to vote for the best final prediction. So what is bootstrapping? So bootstrapping creates bootstrap sample. You can think of this as it is quite similar to what cross-validation is, if you still remember cross-validation, where we are selecting multiple different sets of training data based on our input, right? But what is different from between bootstrapping and our previous data is that one same sample can be sampled multiple times, right? So this is different from cross-validation. Okay. So now bootstrapping creates bootstrap samples. We can say multiple training data sets by sampling the original data with replacement. Okay. So one same sample can be sampled multiple times. So this replacement means that the same data point can be selected multiple times within a single bootstrap sample, not like the regular sampling, the cross-validation. So this is different from cross-validation. This is an example of how these bootstrap samples is being created. Say for example, if let's say we have the original data set over here, we have samples 1 to 10. So as for bootstrap sample 1, 2, and 3, bootstrap sample 1 may contain all of these samples. So we can see that sample 8, 10, and 5, they are being sampled repeatedly to be trained by the first set of 3. And as for bootstrap sample 2, we are selecting a totally different set of samples where some of the samples are repeatedly being picked, and same as bootstrap 3, so far and so forth. So now we are creating different sets of training data to train these 3 to reduce the variance that it is making. Okay? So then there are 3 steps in this bagging methods. First step is creating the bootstrap samples before the training process. So now, after creating the bootstrap samples, what we are doing here is every single bootstrap sample will be channeled into one base model for training. So what we are trying to do here is to train one classifier on each set of bootstrap sample. So each of the model will be learning a set of parameters to produce its prediction. So then, every single model produces one prediction, which is then being voted or averaged by or averaged as the final predictions of all of these K models. Understand? Am I clear? Okay. So now, they should be more or less the same, but they may differ slightly, but they shouldn't be too wrong. So this is the working methodology of bagging, of bootstrap aggregating bagging. Okay, so we mentioned that this bagging takes in multiple sets of training data through bootstrapping process. So the base model will consist of only one same model. What it means here is that we can take the model of our choice, say SVM, and we just want to train multiple SVMs. That is possible. And one of the most famous off-the-shelf bootstrap model is actually the random forest. So what it does here is we are taking a collection of decision trees in order to make prediction. So now this is an example of random forest. So what happens in this random forest is that we create multiple bootstrap samples on our entire data set. So then each of these bootstrap sample will then be channeled into one decision tree to train one decision tree inside the forest. So each tree trains on random subset of sample, which is our bootstrap sampling. Then not just sample itself, every single tree here that we specify is also going to pick random features for splits in its training process. If you still remember how this decision tree how this decision tree is being trained is by creating multiple rules, right? So now these random features will be chosen to create the splitting rules. And finally, each of these three is going to produce one predicted output where it will be averaged or voted as the final prediction, depends on what our task is. If we are doing regression task, then every single output that is, every single predicted output will be averaged as the final output. If we are doing classification problem, so then every single predicted output will be voted, and the voted ones will be our final output. This is how random forest is working in using this bagging mechanism. Okay, so now the point here is that whenever you are training a random forest, you do not have to do any feature selection. You do not have to do any cross-validation, because all of this process is already included in as a part of ensembling methods. So what you need to do is just to train it and to produce the outcome. That is all. And what you need to fine-tune is the estimators, the number of trees that we have to train to get the final output. Understand? So many students will come and say that, okay, so I'm doing a grid search cross-validation on random forest, and it used to crash, system crash, because it's taking too long. That's because random forest itself does not require any cross-validation or grid search. Okay? Yeah? So, yeah, that's a point. So what are some of the pros and cons of these bagging methodologies? So the good thing is it helps to reduce the variance for our prediction because we are taking multiple predictive output and averaging them. So we reduce the variance that leads to improved accuracy and generalizability of our model. So the model is expected to perform well on training data as well as the testing set of data, unseen data. So the downside of this bagging process is that it may not significantly improve the models that are already with very low variance. Yeah? Say for example, if you train a single logistic regression and you find that the performance is not that great. So if you were to stack many logistic regression using this bagging method, it will not help to improve the accuracy. Because what we are trying to do is pretty similar to cross-validation. We are just selecting different set of samples to train and to produce the output. Okay? But this decision tree can definitely be improved because decision tree is a relatively unstable model to start with. Right? That is bagging. So now the second idea about this ensemble methods is boosting. So how does this work? So now boosting is a sequential ensemble method. So different from bagging, bagging trains every single model separately, individually. So one model does not rely on another model. But in this boosting, what happens here is we are using simple model that is built on top of one another. So each model here, they will focus on correcting the errors that is made by the previous one. And this iterative process will help to reduce the overall bias. Say for example, we are starting with one data set and we will train our first base model, regardless of what it is. Then the output of this classifier will be channeled to the next classifier. So the misclassified data will be given a higher weight so that the subsequent classifier can learn the features of our data set a little bit better. So then the output of the second classifier will then be used as the input of the next classifier, where if let's say it is making more and more error, this error will be given further weights so that the following classifier can learn the features even better. So this is very different from how bagging behaves, where bagging trains every single model in parallel. The output is channeled for final voting. But in this boosting, the output of one same model will be used as the input of another model. Okay, so that's the difference between bagging and boosting. So at the end of the day, we will then vote on the final predictive outcome. So now let's take a look at, let's demonstrate on what this means and how this works using a decision tree algorithm. So our boosting methodology, it trains model in sequence. So each model works on rectifying the errors made by the previous one. So let's take an example. So say initially we are starting with one data set that consists of positive points and also negative points, these white color ones. Okay, so every single sample here have one equal weights. They are weighted equally. So now, once we channel this data set into our first classifier, what it does here is, it is trying to define a decision boundary that separates between the two classes. Say, for example, if let's say the first round, it draws this line to segregate between positive and negative. So we know that everything that sits in the pink color box here should consist of negative points. And all of the positive that is sitting in this pink color area will be the wrong prediction, will be error. This error will be given very high weightage. So then, our sample set will change from this manner into this manner. So where we still have all the points here, but the error points, the one that the first model predicts wrongly, will get higher weights. So now they become bigger. Okay? So once it becomes bigger, it will be channeled into the next predictive next model. So now this next model is going to focus on the weighted samples a little bit more. It will try to make these samples correct. And therefore, what it does is, it will draw another line to make sure that these 3 points is included in a correct segment. Yeah? So now, say for example, round 2, this model will then draw one line over here to separate between positive class and negative class. But this time round, we are able to correct the error that is being made by the previous model. However, this model will continue to make some error itself, right? So now, we know that all of every point here is supposed to be positive sign. So all the negative sign that is sitting in this box will then be weighted as the error that it is making. Okay? So as a result, this is the final outcome. Instead of this, we are having now this set of sample where our positive point here is de-weighted and the wrong prediction negative point here is given higher weight. So then this set of sample is going to be channeled into another model. So for another model, this model will then focus on getting all of the 3 samples correct. So if you were to figure out a line that would segregate between the positive and negative points, and ensuring that 3 of these weighted sample is predicted correctly, you will go and draw this line over here. So now in round 3, we can see that, okay, we are correcting the error that is being made by the previous point, but we are making further error that is a little bit smaller. So only 2 points has an error from this side, and one error is seen from another side. Okay? So now, these 2 samples is going to be weighted again. And then, so finally, what we are producing is 3 of this line that segregates between the positive and negative from one side, then another line that would separate between the positive and negative, and finally another line that would separate between the positive and negative, right? So now it is going to take this line, and this line as the final model, okay, to predict, to try to get to all the correct prediction, right? So this is how it works. So if you were to view this from the perspective of sampling itself, this is how it would look like. Say, for example, if we have our original data, 1 to 10 here, during the first round of our boosting process, we can see that now the wrongly predicted ones, the error, will be given higher weights. That means we are giving it higher weights. That means we put this sample more times into the further model, right? So now, in the next round, the one that is being errored output will then be given more weights. So they will be, this model, the next model, will see these samples more times so that it learns the feature a little bit better. And finally, those that are still being wrong will then be trained more times for the next model. This is the general idea of how boosting works. Okay, it is a little bit different from bootstrapping. So it is based on the error which is being made by the previous model. Okay, difference between bagging and boosting. So now, similar to what bagging has to offer, we can also boost using multiple machine learning algorithm, those that we have already learned. But one of those most established methods that uses this boosting idea is ADA boost and also gradient boost. So you will come across all these models very frequently because this model, they are just so good in making prediction. And those are the models that commonly wins the Kaggle competition. So let's take a look at what are the difference between ADA boost and gradient boost. So they are using these boosting methods, but the way that they channel the error from one model to another is different. So in ADA boost, it is one of the earliest, most well-known boosting algorithm. Yes, that's no doubt. So what it does here is it will initialize the weights of all the data points as equal weights initially. So now it trains a decision tree and calculate the weighted error rate of the predicted output. So following from there, based on the error that is tabulated on its output, we are then able to calculate the weight in the ensemble tree. So then we update the weights of the wrongly classified points, and we channel the wrongly classified points, the error, into the next tree. So the next tree here receives the same data set with updated weights, right? And train further, and being trained further. So now how this ADA boost at the end of the day, towards the end of the final tree that it reaches, is that it is going to add up all the weights from each of the tree and multiply the prediction of each tree. So now the tree that has less error will be weighted more. Say for example, if the first tree make a lot of error, so then the predicted output of this tree will be given less weight. Okay, and at one point there will be a tree that is making more correct output than the other tree. So those output will then be weighted a little bit more compared to the other tree. So by having this weighting mechanism, each of the tree, from each of the tree, we will then be able to produce one single output. So the tree with higher weight will have more power of influencing the final decision. Okay, this is how ADA boost work. So each of the tree now receive sample with updated weights. Yeah. So what's the difference between ADA boost and gradient boost? Okay. So now this gradient boost, they are learning from mistakes, but this time round, they do not learn from the error points itself. Instead of error point, what the next tree is learning from is the residual error from the previous tree. What is residual error? It's just the predicted output minus actual output, the square of the value. Okay. So now what happens in gradient boost is that we are training first decision tree. So now we know that this tree is going to make some error. So all of this error, the residual error, will then be channeled into the second tree. So this second tree here, instead of receiving the weighted error sample, what it receives is the residual error. And it is training a model that predicts the residual error. Okay? So now the output of this tree is going to be the residual error of the residual error prediction, which then be channeled into the following tree, so far and so forth. So now at the end of the day, when we make a decision of the final predictive output, instead of using the multiplication and also the summation, what we are doing here in gradient boosting will be taking the first predictive output and plus all the output of the error to make its final output. Okay? So gradient boosting makes a new prediction by simply adding up the prediction of the first tree and the other tree, because from the other tree, what we are trying to predict is the residual errors. Add up to our very original output, that will be our final output. Okay, so this is the difference between Ada boost and gradient boost. So what are some of the pros and cons of these boosting methods? So this boosting method, it is able to reduce the bias to improve accuracy. So this allows us to capture more complex data patterns in our data set, because it is channeling from one tree to one model to another. So again, all the models that performs well on training data will also perform well on our output data here. So one of the major limitation of this boosting tree is if we keep on training this boosting tree too much, it may tend to overfit. Okay, so so this is one of the cons in boosting. So do bear in mind that if we are training a tree, we have to stop where we need to stop to prevent overfitting. Okay, so far we have covered bagging and boosting. Is there any question before we move on to stacking? Okay, all good. So now, quick question. The goal of boosting is to reduce variance in prediction, reduce bias in prediction, improve interpretability, both A and B. It only helps in reducing bias. So in order to reduce variance, we have to make use of the bagging mechanism, because we are using a voting mechanism to try to reduce the variance in prediction, by averaging the output. Okay, so finally, this is stacking. So how do we stack things together? Okay, so the working methodologies, benefits, and also limitation. So now you can think of this stacking ensemble model as a part of neural network. So in neural network, what we are trying to do is to stack multiple neural networks so that it learns the pattern from our data set. So every single neuron is learning. So instead of neuron, this is much more earlier than artificial neural network, where we are utilizing an idea called stacking. So stacking is sometimes also referred to stack generalization. What we are trying to do here is to combine the prediction of a lot of base model, different base model, and we use this meta-learner to produce the final predictive model. So now say, for example, we have three base model: logistic regression, SVM, and decision tree. So three of this model is going to behave very differently because they are undertaking different statistical assumptions, and some of them are non-parametric models. Okay, so the error that they are making is assumingly independent from one another. They will make error but the point that they make error is different. Okay, the way that they make error is different because the assumption is different. And therefore, we will then take the output of every single model and channel it into a meta-learner to produce the final prediction. So now let's take a look at what it is more formally. So stacking combines the prediction of multiple base learner in two-stage approach. So the first stage here is to train our base learners. So all of these base learners have to be trained separately, like what we did in the past 3 practical sessions. We are training every single model separately. So we train a different set of base learner based on original data, training data. We can use all of these types of a model as our base model. So basically, any type of model can be used as different model. So the stage 2 is, all of this model is going to produce one predicted output. If you still remember how bagging makes a decision is by a voting mechanism. So now, instead of voting, what this stacking does is, all of this output, the predicted output, will then turn into the learning feature for our meta-learner. So all of the predicted output will be channeled into the meta-learner to build the final predictive model, which gives you the final output. So instead of using averaging and voting, we are training another model based on the output of every single base model to produce the final prediction. Okay, so this is the general idea of stacking. So we know that we need to have 2 models. It is a 2-stage model, just like a neural network. Every single neuron is learning the feature and producing output. So now, what should be the properties of our base classifier? So these are our base classifiers. So it is recommended to include a very diverse group of classifier. So that means what we are trying to do is to include base classifier which makes different assumptions. Therefore, we assume that they are making errors based on different logic. So with this, we want to increase the diversity of our base classifier. And it is also recommended to choose some of those classifiers which are considerably less stable. So some of the, what do we consider less stable? So the less stable classifiers are usually the non-parametric ones. Non-parametric models means they do not undertake any statistical assumption. For example, decision tree, neural network. Okay? So they are being unstable means that like any single changes in training data can produce very large changes in the model structure. So alongside with decision tree, KNN is also another type of classifier which is relatively unstable compared to logistic regression and LDA, linear discriminant algorithm. Okay, so some of the examples of unstable classifiers are decision tree, neural nets, rule-based method like knife-based, KNN. Okay, this is the properties of base classifier. So now just earlier what we mentioned here is the output of every single model here is going to be the input of our meta-learner. So how does this look like? So the input data set for our meta classifier is formed by the output of all the base learner. This is what it looks like. So now we have the first model output based on multiple training example. Okay, and then we have the output from the second model based on multiple set of training samples. And we have the following ones with multiple training samples. And this is going to be the features of the meta-learner. So our meta-learner, you can just imagine it as another machine learning algorithm where it is taking the output of every single model as its input. So the target variable of the meta learner is going to be the label, which is our common target variable y again. So what it is doing here is trying to learn the features from every single model output to minimize the error between prediction and the actual output. And this is how this meta learner learns. So this meta classifier can be any classifier, and the job of this classifier is to use the information provided by the subsequent base model as its input to make the final prediction. So this meta classifier is trained using the output of the base learner. So as simple as it is. So it is an interesting method to play around with, where you get to train every single model, and at the end of the day, you will package all of the fine-tuned model using this static method to see if it improves the overall accuracy of the model. Okay? Pro and cons. The good thing is, it will usually outperform the individual base learner in terms of accuracy as well as generalization. So the good thing is, we do not have to do any regularization on stacking or whatsoever, because it is just embedded in the way it makes prediction itself. What is it?